Good afternoon, everybody. Welcome to lecture. So today we're going to talk more about electrophilic aromatic substitution and substituted rings and the effects that they have on the position of groups that get substituted onto the ring. So first of all, there's a survey question. There's actually two questions in this survey for today. We'll go over both of them that deal with this topic. So the first question asks, what would you get if you started with this molecule and you put in these conditions and these were your three choices? Which of these would be major products? So what you need to know is that this is a phenol and there's an OH there, and that OH group, the oxygen has lone pairs of electrons, and those lone pairs donate into the electron density of the ring and make it more electron rich, specifically at the ortho and para position. So this is an ortho para director and a strong activator. So the substitution is going to want to happen at the ortho and para positions of that ring, and then this is nitration conditions. So when you put nitric and sulfuric acids together, you get nitronium ion, which is NO2+, and then that is what reacts with the ring, and you get a nitro group attached. So the answer to this one is you get the ortho and the para as a major product, but not the meta. The meta is a much smaller product. It wouldn't be a major product. So the answer to this one is 1 and 3. Then let's take a look at the next one. Has to do with a Friedel-Crafts alkylation reaction. And so it's benzene, and it's reacting with, first, Friedel-Crafts alkylation reaction, whereas an alkyl halide with aluminum chloride, and then in a second step, nitration. So the things you need to know are that, right, this puts an alkyl group on the ring, and this puts a nitro group on the ring, and then you just have to figure out, is there anything else going on? And the thing about this one is this is an alkyl halide that's subject to rearrangement. So when the aluminum chloride attaches to the chlorine, it makes that a primary-like carbocation. It's kind of like a primary carbocation. There's a rearrangement that happens where the hydrogen that's in this tertiary position migrates over, and the carbon here in the position becomes a carbocation, and that's a lot more stable than a primary carbocation. So, so you get a tert-butyl electrophile and tert-butyl cation electrophile, and then that goes on the ring, gives you a tert-butyl group on the ring. So that's step one. So the products have to have a tert-butyl group on them, and that would be either A or C. So then the next thing is nitration. So that tert-butylated ring then gets a nitro group, and the tert-butyl group is ortho-para directing, so ortho or para would be the logical choices. And only para is listed here, not because it's the only possible product, but major product, but because it's probably the most likely, since tert-butyl group is really bulky and would probably block the ortho positions from producing substantial amounts of product. But the meta is not a good choice for major product because the tert-butyl group here is ortho-para directing. So I'm going to submit this so I can show you the feedback on this quiz or survey, because it's pretty good. It was designed, it ends up explaining a lot of stuff. So let's go through and take a look at this. The first question, the answer is C. Structures 1 and 3 are major products. That's correct. The OH group is an ortho-para director. And then for the second of these questions, the solution goes through a little mechanism here, and I'm going to try to make this a bit bigger and discuss what happens. So the alkyl chloride binds to the aluminum chloride. A pair of electrons on the chlorine goes and makes a bond to aluminum, and you get this activated species, which then undergoes a carbocation rearrangement because the chlorine here makes that carbon partially positive, and it's almost like a primary carbocation. So this is one that likes to rearrange where the hydrogen in the position next to the carbon that bears the leaving group, a hydrogen likes to move over with a pair of electrons and the leaving group leaves. That's called a 1,2 hydride shift. That gives this tert-butyl cation, which then the ring reacts with to give tert-butyl benzene. Then the next step is a nitration reaction where you've got this group that's ortho-para directing, and para is a major product. So that's how that one works. So the correct answer for this one is, let's just see what it A, B, C, D. It is A. So let's take a look at these statistics for this. Okay, so the first question, most people got it, C. That's really good to see. And then for the second one, it was the most popular answer. There were a bunch of other answers, but A was the correct answer, and I guess the majority of the people that answered it, that was the one that got the most votes. So we'll work on this stuff. We'll get better at it. As you do examples, you'll learn it in greater depth, and it'll become easier. So, all right. Any questions about the survey? All right. Then let's talk about Friedel-Crafts reactions a little bit more. I want to summarize some of the limitations of Friedel-Crafts reactions because we've said a lot about them, but I want to just in one place tell you about all the things that you need to worry about. Friedel-Crafts reactions are really nice because they make carbon-carbon bonds, and that's an important thing to be able to do. But they come with a huge set of liabilities too. So you got to be familiar with these just to make sure you're not proposing to do a Friedel-Crafts reaction under circumstances where it wouldn't work or it wouldn't work the way you want it to. So here are some limitations of Friedel-Crafts reactions summarized. So the first thing I'm going to do is list limitations of both Friedel-Crafts alkylation and acylation. So there are some limitations that they share. They fail with strongly deactivated rings. We've mentioned this one before. And by strongly deactivated ring, I mean anything that has a meta director on it, anything that's in the list of strongly deactivating groups that are meta directors. They will kill the Friedel-Crafts reaction, alkylation and acylation. Then another thing is they fail with anilines. So aniline is aminobenzene. That's a benzene that has a nitrogen with a lone pair attached. And we talked last time about why that is. It's because the nitrogen lone pair sticks to the aluminum atom. So instead of acting as a Lewis acid and binding to a chlorine to activate it towards the reaction, it binds to the ring substrate, and that kills the reactivity of the ring. All right, and then we've got some other kinds of limitations that are just focused on alkylation reactions. Limitations of Friedel-Crafts, I'll just say FC for short here, alkylation specifically. So these are ones that just bother Friedel-Crafts alkylation, but not acylation. First thing that we talked about is only sp3 hybridized organic halides work, so only alkyl chlorides work. You can't take an aryl halide or a vinyl halide, which is a halogen attached to an sp2 hybridized carbon, and expect that to work. It doesn't work in Friedel-Crafts reactions. Or Friedel-Crafts alkylation reactions. The other thing is carbocation rearrangements, which we saw an example of in the survey question. Carbocation rearrangements. May occur depending on the substrate. If you've got an alkyl chloride that you attach an aluminum to and then it generates a carbocation or a carbocation-like species that can rearrange to become more stable, that will happen. So that's a limitation, can be a problem. And then here's one that's new that we're just going to talk about today because now you understand the effects of substituents on rings. Overreaction is a frequent problem. And I'll say over-alkylation is a common problem, and I'm going to explain why this happens and just get you sort of oriented to it so you can expect it or plan for it, or just be aware of it at least. And the example that I'm going to use to illustrate, oh yeah, question there.
So by the second star, do you mean that like when there's a carbon-cation rearrangement that it stops the reaction then?
Okay, so the question is with this one, does it mean that the reaction will stop? No, it just means you get something maybe different than what you expected. So if you were trying to make a carbocation in a primary position, that's not going to work, for example. So you know, the reaction will give something. It's just the carbocation might not be initially what you had hoped. Or, you know, if it rearranges in a way that's favorable, like if you want that rearrangement to happen, like if you're happy with a tertiary carbocation rather than a secondary, then great. But it can be a problem, you know, if that's not what you want. And we'll talk about ways around that problem in either at the end of this lecture or at the start of the next one, because there are solutions to the problem, but we'll get to that in a little bit. So here's the over-alkylation problem, and I'm going to illustrate it with benzene and Friedel-Crafts alkylation with chloroethane. So chloroethane and aluminum chloride, you get the chlorine bonding to the aluminum, which activates it and makes it into an active electrophile, and then the ring attacks it, and you get ethylbenzene. Okay, no problem there. I mean, that's a reaction that works well. The problem is, though, is that this ethyl group, the alkyl group that you put on, is an activating group. So I'll say here, alkyl groups are activating. And what that means is that this will react faster than the benzene starting material that you want to make into another. You know, basically, if you want the reaction to go from here to here, the product that you make is more reactive than the starting material you used in the first place. So this is more likely to react again than this is to react. Basically, it's a problem where this is going to react again potentially. And since this is an orthopara director, there are a couple of different products that you could get out of this. It would react. If it reacts again, you can get ortho substituted product, or you can get para substituted product, and now you have two ethyl groups on. And the problem with that is now you have two activating groups on the ring. So it's even more reactive. It's even more electron rich, and the reaction wants to happen potentially again. And so these products can react to add another ethyl group. And this is an orthopara director, that's an orthopara director, so there's a few different possibilities. You could get a product where you get an ethyl group there, which is ortho to that substituent. You could get another ethyl group where you get it para to that substituent. And then there's like versions that produce the same thing. Like if you put an ethyl group down here, it's the same as that one. If you put an ethyl group there, it's the same as that one by symmetry. That diethyl benzene can produce these two products as major products of a Friedel-Crafts Friedel-Crafts alkylation reaction. But this one can react again or can react more. And this one would produce this as well, because this would either go here or here or here or here, and those are all identical. So basically, the reaction gets progressively more complicated. As this reaction goes along, it generates more and more products, and these could react further. Eventually what happens is it will grind to a halt due to steric hindrance starting to become a problem. We're going to learn about that. But if you look at it, it's kind of a mess. I mean, you get, you know, it's really causing all sorts of problems. If you wanted to get the best chance of getting a good yield of the mono-substituted product, you would run with the alkyl chloride being your limiting reagent and a pretty big excess of the aromatic ring. With benzene, that's feasible, but sometimes the benzene ring, the aromatic ring, is a complicated sort of high-value species that you just can't toss lots and lots of into a reaction and only have a little bit of it react. So essentially, overreaction is a big problem in Friedel-Crafts alkylation reactions, and it's a little bit hard to avoid sometimes. So that's an issue. Any questions about this business of overreaction?
Is that going to be something we're going to like be expected to do on like the test? Or is this just like to help us understand?
Yeah. So the question is how much of this are you going to need to explain on an exam? What I would say is I wouldn't ask you an open-ended question where I would just say, hey, what are all the possible alkylation products? But what I would want to do is see what are the possible monoalkylation products, and then and there might be a focus question that asks you to predict, what would all the disubstituted products be or something like that. So it wouldn't be like where you have to guess what happens, but usually you get a mixture of a lot of different things. So the way I'll structure the questions on the exam is to give you some guidance as to what I'm looking for, but you just need to know that it's a potential problem. So yeah, that's a good question. I mean, these reactions that sort of produce a lot of different things. You can't. It'd be a big project to list all the possible things that could come out of this. All right. Before we move on from this, though, I want to just explain that with Friedel-Crafts alkylation, this is a problem, but with Friedel-Crafts acylation, it is not a problem. And let's talk about why that is. It's worth mentioning why this is a specific problem with alkylation, but not with acylation. So let's take a look at the Friedel-Crafts acylation reaction and talk about why it is a better reaction, because you can control it a lot more. It doesn't like spin out of control and give a mixture of lots of different products. It typically gives one thing and that's it. And here's why. So if you start with an aromatic ring like a benzene ring, for example, we'll use benzene as a simple example, and you do a Friedel-Crafts acylation type reaction where you put it in an acid chloride. I'll put an R group here just to keep it general. Aluminum chloride. The aluminum binds to the chlorine, activates it. The chlorine leaves, gives you acylium ion as your active electrophile, and then the ring attacks that, and you get an acylated benzene. And the thing about this acylated benzene, though, is that this is a strong deactivating group. The acyl group. So the reaction goes once and stops, because one of the things about Friedel-Crafts reactions is they don't work with strongly deactivated rings. And that's actually kind of a feature rather than a bug, I would say, because in this case, it gives you one thing reliably. And this reaction stops after one acyl group is installed. So it goes once and stops. So it's a better reaction. Friedel-Crafts acylation is way easier to control than alkylation. That'll come in handy later. Now we're going to get into situations that are a little bit more complicated, and what happens if you have two groups on a benzene ring. So we know we have this big list of substituents and what their activating and deactivating effects are, and whether they're ortho-para-directing or meta-directing. But what happens if you have more than one? And this happens a lot because benzene rings and aromatic rings in general, there's a lot of different structural diversity with the class, and there's a lot of interesting aromatic rings out there that have multiple groups attached. So this is all about disubstituted benzenes. How do they react? And what we're going to do is look at a few different situations, 3 different situations, and just try to decide what happens in these different scenarios. So situation 1 is when the 2 groups agree on where the substitution should happen. So what I'd say is when the directing effects of the 2 groups agree, or they reinforce each other. Let me illustrate that with an example here. So here is an aromatic ring that has 2 groups on it. This aromatic ring has a methyl group on it, and it has a ketone carbonyl group on it, and it has 2 groups. So we should consider the effects of both groups. That's one of the things that we're going to talk about in this examining different scenarios, is that you just have to look at each one individually. So the OC, or the CH3 group, is an orthopara director. So from the methyl group's perspective, it wants the reaction to happen at the positions ortho and para to it. So it's going to want the reaction to happen here and here. Those are the ortho positions. The para position, if it weren't occupied, would be a spot it would want to activate. But since there's already a group there, it can't add another one. So basically, the methyl group wants the reaction to happen at these 2 spots. Now, what about this group right here? I'll do that in blue chalk. This is a meta director. So remember what meta directors do. They deactivate the positions that are ortho and para to them. So it's going to make that position partially positive and that position partially positive, but it leaves the meta positions alone. So it's going to be selecting for the positions that are meta relative to it. So I'm just going to indicate that with these blue arrows. So what I'm saying here is that both substituents agreed this is the place to put a group. They both have the same overlapping, reinforcing, directing effects. And so this is a case that's easy. If you were to do a electrophilic aromatic substitution reaction, like say for example a nitration, if you saw HNO3 and H2SO4 listed above an arrow for this molecule, you'd have to remember that this is nitration conditions. Then you'd have to sort out the directing effects of the groups. You'd see that they agree with each other, and the product that you would get out would be the one where the nitro group goes either in either of the 2 positions. By symmetry, they're both the same, so you don't get a different molecule if it reacts on the left side or the right side, because you can just rotate the molecule to interchange those 2. They're not different, basically. But this is the main product, and this would go in really good selectivity. You predict this would be a nice reaction, produce probably just one thing. So there's one example of this. Let's go take a look at another example and go through the analysis. This one will be just another example that shows kind of the same sort of logic. It's a benzene ring that I'm going to be presenting here that has 2 substituents on it. And this one has an OCH3 and a nitro. So let's look at the examples here individually. And I will just start with the methoxy group. That's a strong activating group and an orthopara director. So it wants the substitution to happen ortho and para relative to it. So this is the ortho position relative to that ortho para-director, and here's the para position. So those are the two spots that the methoxy wants to make react. It makes these spots partially negative, and that makes the electrophile want to attack here. Now the nitro group is very much different. It is a strong deactivating group, and it's a meta-director. So it wants the substitution to happen meta relative to it, and the positions that are meta to it are that position and that position. So again, there's this double selection effect where the two groups are agreeing on where the substitution should happen. And then if you had some kind of electrophilic aromatic substitution conditions, like, for example, SO3, H2SO4, you'd need to remember that those are conditions that will sulfonate a ring. They make a sulfonic acid, and that puts a group in either one of those two spots. And I think what I'm going to do is draw this one up a little higher so I have space for the two possible products here that would come out of the reaction. With the OCH3 and the nitro. And one of the two products would be the sulfonic acid group in that position. The other product would be sulfonic acid group in the other activated position. OCH3 here, nitro here, and the group added to that carbon. So two major products. All right, that's the case that's like the most straightforward. But the thing is the groups aren't always arranged in a way that where they agree on where the substitution should happen. Sometimes they are in conflict. They disagree. And so under those conditions, you have to know what's going to happen. And this is the second situation that we're going to talk about. Any questions about this first one, though? Are the directing groups directing to the same positions? Okay. Yeah, that's usually the one that's the easiest to understand. This one is less clear and probably less selective. It's the kind of situation where your reaction's probably not going to work quite as well, but you can predict what a major product will be. So this is situation 2. Directing effects oppose each other. As an example of this, I'll pull up a benzene ring where we have this kind of problem. This is a ring that has two different groups on it, and the OH is orthopara-directing. And it wants the substitution to happen ortho to it. And para, if the para position were open, it would want the substitution to happen there. But since it's got a methyl group there, you don't have to worry about that. And then down here, we have a CH3 group, which I'll highlight in blue. This is also an ortho-para-director. So it wants the substitution to happen in the positions that are ortho to it and para, but that para position is also blocked, so there's no substitution that happens there. So what happens? They're clearly having a disagreement about this. So who wins the argument? And the rule is this. in these situations, the stronger activating group wins out. Basically, since this is a stronger activating group, and I'm going to put that up here, strong activator. And this is an ortho-para director. It's an activating group, but it's a weaker activating group. Its influence is less. They both work by putting partial negative charges on the ring, but since this is a stronger donator, it puts a much stronger partial negative charge on those positions than the methyl group puts partial negative charges on those positions. And so when the electrophile comes by to react with the ring, it sees these as more attractive spots, and that's where it's going to go. So the reaction here, I'm going to do a Friedel-Crafts alkylation reaction. As an example of a reaction that would basically be selecting different positions on the ring. It's going to go to the spot that's activated by the stronger activating group preferentially. So this would be the major product. It's not that you can't get the minor product, it's just there's going to be less of it. And a lot of times these are structured, these questions, to give you, look for the most important thing. What's the big thing that comes out of this? And it would be this. The molecule has symmetry. So in this case, it doesn't matter whether it reacts on the left side or the right side. They both give the same product. All right. Let's take a look at maybe another one of these, just to get more practice. But any questions on this one so far? Is this okay? Just like systematically look at the two different activating effects and decide which one's more important. And you have that list of activating groups, and the order that they're arranged on that chart is the order of their importance in terms of activating. So since the phenol OH group is right towards the top, it has the biggest influence. All right. Here is another example. All right, this one has got, let me see what I wanted to do here. This one has a methyl group and this group. Okay, so what's going on with these? We're going to need to analyze the material or the substituents and decide what their importance is, what their effect is, and what their importance is. So this is a stronger ortho-para director. Stronger than the methyl, which is a ortho-para director, but it's weaker. So the material here, this group, wants the substitution to happen in the positions that are ortho and para to it. The methyl group is ortho-para directing, and its preference is for the reaction to happen here, but its influence is less important, the methyl's is, because it's got a weaker directing effect, so that when you do a reaction with this molecule, and like, for example, a chlorination, you're going to get the reaction happening in these positions preferentially. So the product would be then the chlorine going in either of the two positions indicated here by the orange arrows because they're both equivalent by symmetry. So this would be the major product. Okay, that's the second scenario. More complicated, but certainly manageable. Any questions about that one? All right. This third scenario is just relating to steric hindrance. So talking about what is the influence of steric hindrance in these reactions, because it can make a big difference. So situation 3 is just one where steric strain, steric hindrance can limit products. So I'm going to show an example that illustrates this. And this example is going to start with a benzene ring that's got 2 methyl groups on it. And they're arranged in a meta relationship with each other. And if you do a reaction with this molecule, like say for example, you put in Br2 and Fe Br3, what happens? Well, let's consider both of them. This molecule, or this methyl group, is ortho-para-directing. So it's going to want the reaction to happen ortho, ortho, and para relative to it. I'm just identifying all the positions that it puts partial negative charges on. All right, then let's look at the other methyl group. This methyl group over here is an ortho-para-director. It wants the reaction to happen in the ortho positions relative to it. Which would be these. So we got a situation where we've got doubly activated spots. This molecule's got the same positions activated by both groups. So you might expect to get a mixture of 2 products. Here, an reaction on the left or the right carbon is the same by symmetry for these 2 spots. And then maybe this spot too as well. But it turns out that the top spot is too hindered. Because the 2 methyl groups are kind of bulking up that spot, there isn't any reaction that happens up here, even though those carbons are well activated electronically. In other words, there's a lot of partial minus charge there. That would be a good spot for an electrophile to go if only it could get close enough. But it can't because the groups are getting in the way. So what I'm going to say is this spot up here is too crowded. And so what you get then is the spots that are sterically available or accessible and are activated is where the reaction happens and where the group goes. So the major product in this reaction is this. And it's the same if I would have drawn the bromine on the other side because they can be rotated and they're the same and superimposed. So this is an example of steric strain, steric hindrance limiting the products that can come out of a reaction. And if you want a take-home message, just don't do electrophilic aromatic substitution when there's 2 groups flanking a position. So just this sort of think of them as just blocking that spot effectively enough that you just don't get substitution there. All right. So that is like a way to handle these situations where you've got multiple reacting or groups influencing a reaction. Questions on this? Yes.
What deactivating group that influence the same position?
Yeah, so the question is what happens when it gets confusing? So it's a really good question. It's like what was asked specifically is if you have an activating group and then a deactivating group that's opposed to it, then they're relatively, their effects basically kind of offset each other. Those situations can happen in reality, and what you probably get in those situations is a mixture of products. It doesn't really have a favored product or not. So I won't present questions like that on an exam where the outcome is unclear, because if you can't figure it out, probably you'd get a mixture of things. There'd be multiple products and there wouldn't be like a major product. It's a good question. It's, what kinds of questions can you reasonably answer? And the way I'm going to do it is I'm going to structure the questions such that they'll fall neatly into situation 1 or 2 or 3, or maybe you have to use logic from different scenarios, but basically you'll be able to explain all the questions that you're going to get based on these 3 situations. Another question.
So this situation 3 would still work if it was like a methyl group and then another like alkyl group, like ethyl or something.
Right, yeah. So methyls is kind of the most forgiving of all the examples. So if you put an ethyl group here, you'd still have the same problem, but it'd be more pronounced. That spot would be even more crowded. And then another sort of thought about this, and I'll just put this over here. We'll talk about this on the other board for a little bit. Steric strain can come up in other situations too, like if you've got groups that are like a single group that's really, really big. For example, a tert-butyl group. Tert-butyl is remarkably large. It doesn't always look that way when you draw it as a skeletal structure, but remember, these are methyl groups and they take up lots of space. It makes the ortho positions especially hard to access, so it's pretty tough to do reactions next to a tert-butyl group. And so if you do some kind of electrophilic aromatic substitution reaction with this molecule, I'll just do nitration as an example, you're gonna probably not get very much ortho. Major product. So what I'll do here is say ortho positions are crowded. In this case, because the tert-butyl group is just really big. There's another place where steric strain comes into play, and that's a lot of times with Friedel-Crafts acylation reactions. They tend to be fairly para-selective because for whatever reason they're kind of sensitive to steric strain. So here's an example that you are familiar with from lab last week. So we did a reaction where we took anisole and we put it in with an acylating agent. We use propionic anhydride in the lab, but you could use an acid chloride too, which is more consistent with what the textbook talks about. For pretty much the textbook just talks about acid chlorides and aluminum chloride, but the way we did it with propionic anhydride and a Bronsted acid would, should work the same way here. And that's that para is the major product. So specifically for Friedel-Crafts reactions, and I mean, this reaction worked so well for us under our conditions that we didn't even see the ortho. So what I'll say, just as a side note, is that Friedel-Crafts acylation is especially para-selective. So if you've got an activating group on your ring and it's an ortho-para director, the para is going to probably be your major product most of the time. It's honestly, it's kind of complicated with some of these reactions where different groups will have different directing effects. I mean, it's not quite as simple as we make it out, but we're putting as much theory as we can to give you a good solid set of rules so that you can predict a lot of things really well without getting too deep into the weeds of what exactly does every group do in every situation. So that's enough to know about steric influences. Okay, then you get into situations where, okay, let's put our knowledge to use and make some electrophilic aromatic substitution reactions work for us and build some molecules. So synthesis. And that is where we're headed next. Synthesis of benzene derivatives. This is a new section. Synthesis of benzene derivatives. There we go. So the order of substitution makes a big difference. That's the take-home message. The order of reactions is critical. So here's an example of that. So suppose you wanted to make, starting from benzene, you wanted to make a molecule where you had a bromine on the ring and a nitro group on the ring. So your job was to start with this and make that. And what you would think about is, well, I have to put a bromine on the ring. So I know, like for example, based on my knowledge of electrophilic aromatic substitution, I know this goes on using Br2 and FeBr3. And then, I know this nitro group, the recipe for putting a nitro group on the ring is HNO3 and H2SO4. So you're going to need to do these two reactions. But look what happens if you do them one way versus another. If we do a nitration first, if we first do HNO3, H2SO4, we put a nitro group on the ring. Okay, the problem with this is that this is a meta director. So the next group that goes on is going to go in the meta position. So when you do the second step, you do your Br2 and FeBr3. The result isn't this. It goes Br2, FeBr3. You get the meta substituted product. Nitro and bromine are not where you want them to be relative to each other. So, that's because you put the meta director on first, and then the second reaction gives a meta product. So the way to fix that is first put on the bromine, because the bromine is an ortho-para director. So in other words, if you've got a ring that has just bromine on it, the next reaction that you do, the nitration, is going to put it in the right spot. So if you do Br2 and then FeBr3 together at the first step, you'll get bromobenzene. And then since that's an ortho-para director, when you do the nitration, NO3 H2SO4, this will be one of your major products. You'll also get, in addition to this, you'll get, an ortho version of this probably. You'll probably also get this as a major product. But at least, let's see. The way we did this is we put the bromine on first, so I'll put that up in that position. And then nitro in an ortho position. This isn't the desired product the way I set the question, but at least the product is a major product. So if your goal is to make this is a reasonably good way to get there. You would produce some of this, but at least that's a major product. If you went the other way and did the nitration first, you wouldn't get any of the desired product. It would be not produced, you'd just get this. So strategy comes into play when you're trying to plan reaction sequences to build a specific structure. And here's an example that's maybe got a little bit more practical value. It isn't just a theoretical exercise. It's a real molecule that has significance. So there's a molecule out there called bupropion. That's the generic name for it. Brand name is Wellbutrin. It also goes by Zyban. So it has a bunch of interesting properties. It is an antidepressant that works differently than most of the SSRI, serotonin reuptake inhibitors. It's got a different mechanism. And it's also good for smoking cessation. So it's a molecule that does a couple of different things. Zyban is what it's sold as, is a smoking cessation aid. And then Wellbutrin is its brand name for treating depression. But what makes it interesting for our discussion is it has this structure. It's got an aromatic ring with two groups, and they have a meta relationship. So what I'm going to do to make this a little bit simpler and easier to look at is I'm going to take this whole big group here, and I'm just going to call this R. So I'm going to simplify it down a little bit so that we can appreciate the groups by themselves without getting distracted by all the other stuff that's attached to the carbonyl group here. It matters. It's not that it's insignificant, but it's just I want to simplify it for purposes of this discussion. So there's our target molecule. We want to make this Wellbutrin molecule. We got a disubstituted benzene. It needs a chlorine and it needs an acyl group. So we're going to need to do Friedel-Crafts acylation to put this group on, and we're going to need to do chlorination to put that group on. So if we started with benzene and we first did chlorination, Cl2 FeCl3, we would get a chlorine on the ring. And all the positions on benzene are equivalent. So I'm just drawing it in the spot where I drew it over there to align it with the desired product. And then if we did Friedel-Crafts acylation and we used an acid chloride, an aluminum chloride, we would not get a meta product. We would get a mixture of two things, neither of which is what we want. We would get, because chlorine is an ortho-para director, we would get the acyl group in an ortho position as one of the products, which is not what we want. And we would also get probably acyl group in the para position, which is also not one of the desired compounds. So this would be a bust. This wouldn't really work at all. So that would be a fail. But if you just change the order of the groups around, it makes a huge difference, because now if you do your Friedel-Crafts reaction first, you put on an acyl group, which is a meta director. So now we've got an acyl group on the ring, and that is going to influence the reaction to go in the meta position in the next step. So we'll do, in the second step, the chlorination reaction, Cl2 and FeCl3. And now, because that's a meta director, the reaction is going to work properly. It's going to give the chlorine in the spot that it needs to be to have the right structure to be this drug. So this route works. This route does not work. It doesn't work correctly. You get a product, you just don't get the right one. So the point is when you're trying to do a multi-step synthesis, a sequence of reactions, you have to plan the reactions so that you get the right substituent at the right time to direct the next reaction to go in the right spot. So a lot of times what people will do is look at the reaction backwards. Rather than starting with benzene and thinking through ahead of time, you might look at this molecule and say, well, okay, I got two groups here. This is a meta director. That's an ortho-para director. What would I want to be my last reaction? Well, I would want to have the meta director on and then do a chlorination so that the chlorine goes in the correct meta spot. So thinking in reverse, this is sometimes called retrosynthetic analysis. And it's a way of, like, rather than starting from the start of a synthesis and thinking to the end, start at the end and work your way back to the start. And it's backwards thinking. It can sometimes be a really effective problem-solving strategy. So we will continue to look at examples of this and look at that. What we're going to do, I don't think we really have time to start it today, but next time when we come back, we're going to look at reactions of side chains of benzene rings, which essentially just gives us more options for groups to put on the benzene ring, so we can synthesize a wider array of substituted benzenes. Then we're going to put it all together and make a lot of different benzenes, like benzenes with groups in different spots that have different interesting reactivities. So we'll talk about that on Friday. So I will see you then.